Have you ever wondered how massive industrial facilities actually optimize their energy? Or, are they just literally burning through their profits? Honestly, it's the one question that separates the highly profitable operations from the absolute money pits. So, welcome. If you're a focused learner looking to uncover the hidden mechanics of industrial energy loss, and more importantly, efficiency, you are in exactly the right place. In this explainer, we're going to embark on a conceptual factory tour. We'll walk the exact path that energy takes right from the moment a fuel is ignited all the way out to the exhaust exiting the chimney. Let's get into it.
Our tour today is called the Industrial Energy Life Cycle from Spark to Stack. We're going to break down the highly complex thermodynamic realities that plant engineers have to battle every single day. And to do this, we'll actually look at direct evidence from Industrial Energy Manager certification exams, so we're seeing exactly what the absolute experts are expected to know. It's going to be an incredible journey of pressure, heat, and just relentless optimization. Here is our quick tour itinerary for today. First, we've got the secrets of efficient combustion. Second, mastering the steam cycle. Third, inside the industrial furnace. And finally, number 4, the art of heat recovery. Okay, let's dive straight into Section 1, Secrets of Efficient Combustion. We're starting our tour right at the burner. And to really grasp what's happening here, you have to understand something called the stoichiometric ratio. Now, this is the exact, perfect theoretical amount of air you'd need to completely burn a specific fuel. So, for example, to perfectly burn 1 kilogram of pure carbon, you need exactly 11.6 kilograms of air. No more, no less. Now, in a perfect world, that is all you would use, right? But out here in the real world of massive industrial boilers, well, perfect mixing is basically impossible. So engineers actually have to pump in what we call excess air just to make absolutely sure all the fuel burns. Because if they don't, they're just wasting fuel as unburnt carbon. And what we're looking at here brilliantly illustrates how the actual type of fuel dictates that excess air. Natural gas, that is the gold standard. It mixes so incredibly easily with air, so it requires the absolute lowest amount of excess air. But on the flip side, solid fuels are way harder to burn efficiently. However, there's a workaround. If you grind coal down into a super fine dust, what we call pulverized coal, you can actually achieve the minimum required excess air for a solid fuel. And this is a huge deal because the less excess air you use while still getting complete combustion, the less heat you waste warming up useless nitrogen that's just going to fly right out the chimney. Which naturally brings up a really fascinating question. If we want to be perfectly efficient, why can't we just cool that exhaust gas all the way down to 0 degrees and capture every last drop of heat before it escapes? I mean, it sounds like common sense, right? Why waste it? Well, thermodynamics and chemistry have a pretty harsh reality check waiting for us. So here is the crucial point. It's something engineers call the sulfur limit. You see, a lot of industrial fuels, especially things like furnace oils and coal, naturally contain sulfur. When you burn them, they form sulfur oxides. Now, if you cool that exhaust flue gas too much, that gas actually condenses into a liquid. And because of that sulfur, the liquid is a highly corrosive acid dew. It will aggressively eat right through the metal pipes and the chimney. It's a nightmare. Therefore, the sulfur percentage in the fuel actively sets a hard, non-negotiable lower limit for your flue gas temperature. You literally have to throw some heat away just to protect your own equipment. Crazy, right? All right, moving right along to Section 2, Mastering the Steam Cycle. We are moving out of the combustion chamber now and into the high-pressure pipes. Now listen, if you take away just one golden rule from industrial plant engineering today, let it be this one. Steam should always be generated at the highest pressure possible and utilized at the lowest pressure possible. By generating it at super high pressures, the steam takes up significantly less volume. That means you can transport massive amounts of energy through much smaller pipes, which obviously saves a ton on infrastructure. But why use it at low pressure? Well, to answer that, we have to talk about latent heat. Latent heat is basically the thermal energy required to change water into steam without actually changing its temperature. When steam condenses back into water on a piece of process equipment, it releases this massive payload of latent heat. And here is the real trick. As steam pressure drops, the amount of latent heat available actually increases. So, using low-pressure steam gives you the absolute biggest bang for your buck when you're heating an industrial process. Now, take a look at the large 0 here. This is wild. If you just keep increasing the pressure of steam, you eventually hit what is known as the critical point at exactly 221.2 bar. At this extreme pressure, the boiling point of water is incredibly high, but the latent heat of evaporation drops to absolutely zero. Zero. The water just instantly turns into a vapor without needing any of that phase change energy at all. Okay, so let's see how all of this builds into real-world energy recovery. Boilers are constantly boiling water, obviously, which leaves behind these really concentrated solid impurities. To stop the boiler from clogging up, engineers have to perform a continuous blowdown. They basically drain out some of this hot, dirty water. But that water is under high pressure and it's packed with energy. We can't just waste it. So first, they remove that continuous blowdown. Second, as this high-pressure water hits a lower pressure tank, a portion of it instantly flashes into pure high-pressure steam. And finally, step 3, they recover this flash steam and route it directly into a deaerator. That's a crucial device that uses the heat to basically boil off oxygen and dissolved gases from the incoming feed water. It literally stops corrosion before it even has a chance to start.
Okay, let's step into section 3, inside the industrial furnace.
So, leaving the boiler room, we are heading straight into the manufacturing core. And let me tell you, operating a furnace is not just about cranking up the gas. It's a super delicate balancing act. You absolutely have to maintain a slight positive pressure or draft inside the heating zone. If it goes negative, freezing ambient air gets sucked right in through the doors, instantly ruining your efficiency and oxidizing the metal stock you're trying to heat. Furthermore, at these extreme temperatures, the vast majority of heat transfers into the product via pure thermal radiation. Because of this, engineers apply these special high-emissivity coatings to the inner surfaces of the furnace. This massively boosts the wall's ability to radiate heat directly back into the product. Of course, none of that heat even matters if your furnace literally melts itself, right? And that is where refractories come in. These are highly specialized heat-resistant bricks. The choice of brick depends entirely on the chemical nature of your process. As you can see, magnesite and dolomite are basic in nature. Alumina acts as a neutral refractory, and silica is highly acidic. It's Chemistry 101. If you use an acidic brick in a process that generates a basic chemical slag, that brick will literally just dissolve. The way you actually operate the furnace also completely dictates how you insulate it. Let's compare batch furnaces, which are heated up and cooled down for every single load, against continuous furnaces that just run nonstop for months. If you use really heavy bricks in a batch furnace, you are going to waste massive amounts of fuel just heating up the actual bricks during every single cycle. Therefore, in batch furnaces, lightweight ceramic fiber insulation is an absolute game changer for maximizing your fuel savings. It has incredibly low heat storage, which means your expensive fuel heats your product, not your walls. And that brings us to our final stop, Section 4, the art of heat recovery. In this final stage of our tour, it's all about how clever engineering captures the leftovers. A huge part of this is cogeneration, which just means producing two forms of energy from a single fuel source. In a topping cycle, the fuel is burned primarily to spin a turbine and make electricity. Then, the leftover exhaust heat is used for industrial processes. But in a bottoming cycle, it's the exact reverse. The fuel is burned primarily for a massive high-temperature process, think like a giant glass-melting furnace, and then the leftover exhaust heat is captured to produce byproduct electrical power. The numbers behind this kind of heat recovery are honestly staggering. Just preheating the incoming combustion air using waste exhaust gases by a mere 100 degrees Celsius will directly save you 5% on your total fuel bill. 5%! Now, in a factory spending millions of dollars on coal or natural gas every single year, that 5% saving is enough to completely transform the profitability of the entire company. It's massive. And to actually achieve this, modern facilities deploy some truly incredible technologies. Heat pipes use internal capillary wicks and vacuum-sealed fluids to transfer thermal energy up to 100 times more effectively than solid copper. Thermocompressors use high-pressure mode of steam to literally suck in and upgrade useless low-pressure waste steam back into a fully usable state. And fluidized bed combustion, or FBC boilers, actually burn coal inside a floating bed of limestone. Why? Because that limestone chemically captures those nasty sulfur emissions right inside the boiler itself. So, we have toured the combustion chamber, we've mastered the steam cycle, survived the furnace, and successfully recovered the waste heat. But I want to leave you with a final, kind of provocative thought here. After millions of dollars of engineering and optimization, if just a single $50 mechanical steam trap fails in that piping network, it can leak live steam 24 hours a day. How much of that carefully recovered energy simply vanishes into thin air just because of poor maintenance? True efficiency isn't just about brilliant design and thermodynamics, it's a relentless system-wide battle every single day. Thanks so much for exploring the industrial energy life cycle with me. Catch you next time.